Staring out over the ocean like a forlorn puppy or an incandescent light bulb, the future of your education is here in Physics 122. In this course, we are going to work fairly extensively with the concept of electric charge. Electric charge is the stuff in electromagnetic problems. Even though we work with electric charge a lot in this course, we're never really going to define fundamentally what electric charge is. If you don't like this idea, think about how we treated mass in Physics 121. We worked with mass a lot. At some point, we said you could think of mass as an object's inherent resistance to being accelerated. But that tells us more about a property of what mass does than fundamentally what mass is. And in a very similar way, we're never really going to define fundamentally what electric charge is. Similar to mass, I will say that electric charge is a property of a particle. Some particles will have some electric charge. Different particles might have different electric charge. Electric charge is designated by the symbol Q. Usually, electric charge will be designated with a lowercase q, but you will encounter scenarios where electric charge is designated with an uppercase Q as well. Charge, as I said, is the unit of stuff in electromagnetic problems. Unlike mass, charge can be positive or negative. There are also particles with zero charge. The metric unit of charge is the Coulomb. One electron, one tiny fundamental particle, has a charge of negative 1.6 times 10 to the negative 19 coulombs. So now when we work with problems in physics, we will have four base SI units to consider: kilograms, meters, seconds, and coulombs. Back in 121, when we were talking about force is measured in newtons, but newtons are F equals ma, kilograms times meters over seconds squared. So a newton is really just a certain combination of kilograms, meters, and seconds. In this course, when we talk about electric current or voltage or magnetic fields, these are just going to be units that have their own names, such as amps or volts or Tesla, but fundamentally, all of these units are just a certain combination of kilograms, meters, seconds, and coulombs. One electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. If I am working on a problem that involves fundamental particles, writing this number over and over could become very tedious. So to make our lives easier, let's invent a new unit of charge. This new unit of charge will be based on the fundamental particles of nature, and we'll call this new unit of charge the elementary charge. We'll designate the elementary charge with the symbol lowercase e, and we will say that the elementary charge is the charge of a proton. Therefore, I could say that E is equal to 1.6 times 10 to the negative 19 coulombs. And I could say a proton has a charge of plus E and an electron has a charge of minus E. Part of the utility of working in this convention when we are looking at individual particles is that in nature, charge only occurs in discrete units. As far as we know, you will only find objects that contain an integer multiple of the elementary charge E. In other words, if you come across an object, that object might have a charge of 2e or 15e or negative 376e. You will never, as far as we know, come across an isolated object that contains a fractional multiple of the elementary charge. You'll never come across an object that has a charge of 1/3 e or negative 3.75 e or anything of that sort. Now, there are some models and extensions of physics that allow for the existence of these fractional charges, but these are all speculative right now. None of them are confirmed, and this is beyond the scope of this course. A conductor is a type of material that allows electric charges to flow through them. Now, you might ask, what is special about a material that allows an electric charge to flow through it? Because not all materials allow electric charges to flow through them. A common example of a conductor is a metal. So we could ask, what makes a metal special? And we could imagine if we were to take a microscope, zoom in on a piece of metal and look at its atomic properties, we would see something that is often referred to as the electron C model. Let's imagine that we take our microscope, we focus on a piece of metal, we look at the atomic structure of the metal, and if we were to zoom in, we would see a lattice or a regular arrangement of positively charged ions. Now, by lattice, we mean that there is a certain pattern to the arrangement of the atoms in the metal, and those atoms are repeating over and over and over again. Also, these atoms are ionized. These atoms will have a positive charge. Now, how much positive charge do these ions hold? Well, it depends on the particular metal. Copper or zinc or gold or zirconium might all have different charges to their lattice ions. We're also going to assume that these ions, these positively charged atoms that make up the metal, are for the most part locked in place in the lattice. They're not allowed to move around in any significant manner. Now, we focus on the lattice that all these atoms are arranged in, and we notice that there are a lot of electrons just flowing, zooming about between the ions in these lattice. We call these the free electrons or the C electrons, and we notice that these electrons are not really attached to any one atom in particular. They're just kind of flowing between them, attached to all of the atoms, if you will. So if we were to zoom in, we might see something like this. The large red circles are the lattice ions. All of the lattice ions have a net positive charge, and flowing between them, sometimes bouncing off the lattice ions, are the electrons. The free electrons are the charges that move through a conductor. Overall, this conductor will possess no net charge. If each ion in the lattice has a charge of +1, then for every ion in the lattice, there will be one electron somewhere in the C. If each ion in the lattice has a net charge of +2e or +3e, then you will have 2 or 3 electrons for each atom, each ion in this lattice. So overall, the conductor is neutral, but the arrangement of the ions that have the positive charge and the electrons that have the negative charge is not identical. Now, you could imagine, and we will describe in a future lecture how you might set the scenario up, that maybe all the electrons decide to suddenly move in a certain direction on average. If you just look at the atoms and you see 100,000 electrons move to the left and 100,000 other electrons move to the right, then you would say on average there was no net motion of the electrons. But if instead you saw 105,000 electrons move to the left and 99,995 electrons move to the right, then you could say there was a slight preference to the direction that the electrons are moving. And when this occurs, we would say that a current is flowing. We'll discuss more on this later. An insulator is an object that is not a conductor. Charges can flow through a conductor, charges cannot flow through an insulator. It is possible to place electric charge on an insulator, but once you place that electric charge on the insulator, the electric charge is just going to be stuck there. It won't be able to move around at all. Copper and other metals are examples of good conductors. Rubber is a good insulator because rubber does not let charges move through it. One way that charged objects can interact with each other is via the Coulomb force. Let's suppose we have two particles that we will label particle 1 and particle 2, and we're going to place these two particles on a coordinate system. We will say that Q1 is the charge of particle number 1 and Q2 is the charge of particle number 2. And from looking at this picture, we see that there is some separation between these two particles. So we will define r as the distance between these charged particles. Now, we are going to work with r, and in the equation that I'm going to show you in a moment, r does not describe a radius. R describes a separation or a distance between two objects. The strength of the Coulomb force between two charged objects is given by the equation 1/4 pi epsilon naught times Q1 times Q2 divided by r squared. Now, epsilon naught is a fundamental constant of nature. Epsilon naught is one of those important numbers that makes reality behave the way that it does in the universe. And ultimately, epsilon naught is just a constant. So it is a number that you could just go to the back of the book and look up in a table, or a number that you'll be given on an exam. If I look at this equation very strongly might remind us of the gravitational force that we learned about in Physics 121. The strength of the gravitational force is G times m1 times m2 over r squared. The Coulomb force looks very similar to the gravitational force. Instead of the mass of particle 1 and the mass of particle 2, we have the electric charge of particle 1 and the electric charge of particles 2. We also have 1 over r squared. The gravitational force gets weaker and weaker as the particles become further and further away. We have a 1 over r squared in the Coulomb force. The Coulomb force gets weaker and weaker as the particles get further and further away. In the force of Newtonian gravity, we have Newton's gravitational constant, big G. If I look at this equation, 1 over 4 pi epsilon naught itself is going to be a constant. The combination of several constants itself will be a constant. 4 is a constant, pi is a constant, and epsilon naught is a constant that has some units attached to it. So if I want, I could make my life a little bit more convenient when I use the Coulomb force by defining a new constant. I'm going to call this new constant K. And K is equal to 1 over 4 pi epsilon naught. It's just a little bit smaller than 9 times 10 to the 9. It has units of newtons, meters squared over Coulomb squared. And when I introduce this new constant K, the Coulomb force becomes K times Q1 times Q2 divided by r squared. Sometimes you will see that this constant K is referred to as Coulomb's constant. And a lot of the way we think about Coulomb force problems is going to be very similar to the style of thinking we used when we solved gravitational force problems. So we have Coulomb's force, and the equation written above on this slide, in my opinion, is not the best way to write the Coulomb force. In a few slides, I'm going to present a more general equation that I think is just nicer to work with. However, this equation is still true. The reason for this is this equation describing the force between charged objects only applies when you have 2-point charges. So if you have 2-point charges, you could go ahead and use the Coulomb force. But what if you don't have 2-point charges? What if you have a point charge that is next to a ring of charge, or a point charge that is next to a very long wire and there's charge lying all along that wire? That's essentially a point charge next to a line of charge, or some interesting configuration. If that is what you have, then the Coulomb force doesn't really apply very easily, and we need a better equation or a more general equation to work with. So I just want to point that out, that while this equation is very useful describing the strength of the force between point charges, there is, in my opinion, a better equation that we're going to introduce soon. So the Coulomb force is the force between charged particles, and we have the magnitude of the Coulomb force, but what about the direction of the Coulomb force? Well, unlike gravity, the Coulomb force could be attractive or it could be repulsive. If Q1 and Q2 have opposite signs for their charges, one charge might be positive, the other is negative, or vice versa, then the Coulomb force is going to be attractive. If Q1 and Q2 have the same sign, both charges are positive or both charges are negative, then the Coulomb force is going to be a repulsive force. So you could contrast this with gravity, which was always an attractive force. So how are we going to actually think about this? Well, in my opinion, when you are solving problems using the Coulomb force, I think for the purpose of what we do in this course, this will be a relatively easy strategy. First, don't worry about the signs of the charges. Just calculate the strength or the magnitude of the Coulomb force on a charged particle. For this step, you could temporarily pretend that all the charges are positive. K is a constant of nature, about 9 times 10 to the 9. R squared is the distance squared between the charges, and Q1 and Q2 will often be given in problems. So we could go through a calculation, we find the strength of the force between these charges. Next, let's now look at the signs of the charges. We will ask ourselves, do we expect the force to be attractive or do we expect the force to be repulsive? After we determine whether the Coulomb force should be attractive or repulsive, we will assign a direction to the force on the particle that we are investigating. Now, when I consider the Coulomb force between two particles, be careful about which particle you want to know the force on. By that, I mean, let's suppose these particles have opposite signs. So particle 1 and particle 2, one of them will be a positive charge, the other will have a negative charge. Because the charges are opposite in sign, that tells me the force between them should be attractive. If I am asking about the force on particle 1, the force on particle 1 would be up and to the right. However, if I am asking about the force on particle 2, because the force is attractive, the force on particle 2 will be down and to the left. So when you are working through Coulomb force problems and you need to assign a direction to the force on a particle, make sure you're being careful to be consistent with what particle you're talking about. To finish off our discussion of the Coulomb force, remember that forces are vector quantities. This means that the Coulomb force will have an x component and a y component, and in principle, if we want, we could assign a z component to the Coulomb force also. Furthermore, if we have several forces all acting on an object, we need to add those forces as vectors, not as scalars. It is not enough to just add the strength of the forces. We need to account for the fact that the forces could be directed or pointing in different directions. So to demonstrate this idea, let's suppose we have a charged particle. Here is my charge. I chose to draw it in the fourth quadrant and it happens to be a positive charge in this picture. Now let's say my particle is in the vicinity of several other particles. Some of these other particles might be closer to my particle, some might be further away. Some of these other particles might contain a lot of charge, others might contain not so much charge. Also, the signs of these other particles could be positive or negative or some mixture of the two. So here are 4 other charged particles in the vicinity of my charged particle. Each of these other charged particles will attract or repel my charged particle, and the strength of that attraction or repulsion will be given by the Coulomb force equation up here. I expect if the particles are close to my particle, that will tend to increase the force because of the 1 over r squared dependence of the Coulomb force. I expect if the amount of charge the particles contain is large, that should also tend to increase the strength of the Coulomb force. The negative charges will tend to attract my charge. The positive charges will tend to repel my charge. So each of these 4 charged particles will attract or repel my particle, and the 4 forces of attraction and repulsion on my particle might look something like this. If I want to know the net force on my particle, I need to add these 4 forces as vectors together. And when I do, I find a net force that looks something like this. If you want, you could go back to section 3-4 to review vector addition in the textbook, and we will now go on to some practice problems on the Coulomb force.